I'm Mark Beach from the University of Bristol. In the next 20 minutes, I will provide an overview of the UKRI EPSRC SWAN Prosperity Partnership and a deep dive in assessing and mitigating RF cybersecurity vulnerabilities in low-cost IoT. As I will explain, SWAN is a collaborative research project, with this presentation embracing on many of the activities of the consortium. I would, however, like to acknowledge the worthy contributions from Manish Nair, Wael Bukli Hassan and Tommaso Capello in the preparation of this presentation. In terms of what follows, firstly I need to put into context wireless or radio-based cyber attacks and introduce the concept of the RF open attack surface. As you will see, this provided the motivation for funding by the UK government and industry, the Prosperity Partnership in Secure Wireless Agile Networks, or SWAN, which I will explain alongside our 4 key research challenges. With a wireless focus, RF pen testing is one of our key tools, and we have been using LoRaWAN as our first candidate air interface technique. Using the instrumentation in our RF pen test facility, we can fingerprint the waveforms emitted by individual sensors, and with machine learning, we can aid our classification methodology. Finally, I will say a few words regarding our city-wide LoRa deployment, as well as some points you may wish to take away from this presentation. Cybercrime is often associated with the theft of data, and there are considerable efforts made to ensure that core networks are safe through encryption and authentication. However, with wireless-based systems such as satellite navigation, the channel between the transmitting and receiving antennas can be attacked. Here we have a radio frequency or RF open attack surface which is vulnerable to cyber intrusion. For global navigation satellite services, there are examples of ships being rerouted by adversaries in order to steal precious cargoes. Within SWAN, we are initially focusing on critical infrastructure such as chemical plants, where low-cost wireless sensors are being deployed with potential vulnerabilities to cyber attack. It is this RF open attack surface which is the subject of SWAN's 5-year programme of collaborative academic and industrial work. This is a rich mixture of theoretical research, analytical analysis by simulation, as well as significant degree of experimental work both in the laboratory and the city of Bristol. As I've already mentioned, SWAN is a joint industrial, government and academic research programme addressing the creation of secure wireless agile networks that are resilient to both cyber attacks and accidental or induced failures. We are funded through the 3rd call for UKRI EPSRC Prosperity Partnerships, with an overall remit to transform the way people live, work and travel. We are one of 6 projects funded with an overall budget of 6.1 million, and we started in February 2020, headfirst into COVID and lockdown. Despite this, with our partners, Toshiba Europe Limited, through their Bristol Research and Innovation Laboratory, Rope Manor and GCHQ, we have been able to bring our teams together, initially virtually, but now in person, to commence delivering holistic solutions for a productive, healthy, resilient and connected nation. These goals were at the heart of the 3rd call for Prosperity Partnerships. SWAN's research programme will thus identify vulnerabilities in RF interfaces, develop techniques to detect and mitigate against the effects of cyber attacks. And with the ever-increasing use of software-defined radios, we will create the analog technologies to flexibly partner with digital SDRs. Finally, our overall remit is to create a more resilient and secure communication infrastructure. As with all prosperity partnerships, at the outset we had to define a series of research challenges. The first of these is threat synthesis and assessment, thus addressing the vulnerabilities of RF interfaces, understanding the mechanisms of RF cyber attack, as well as synthesizing the impact on critical infrastructures. Here we adopted and modified Microsoft Stride cards for the cyber assessment of computing platforms, with Roke's RF Stride card deck aiding our analysis in wireless cyber assessment. Our second challenge is RF cyber defense and detection, with a focus on scalable solutions which are both power efficient and cost-effective, as well as the creation of more robust waveforms and protocols and the potential application of spatial or MIMO signal processing. For this, we needed a candidate air interface to take our work forward. We have chosen LoRaWAN as our first radio air interface technique to study, due to its widespread adoption as a low-power, long-range IoT solution with a plethora of applications, including those in critical infrastructure. Furthermore, there are numerous documented cases identifying the weaknesses of LoRa, thus justifying our selection. Back to SWAN's research challenges and our third topic of cyber secure radio. Through the design of architectures such as low noise amplifiers, initially based on a Cascone architecture and then enhanced for increased adjacent channel blocking protection through the application of third order derivative based superposition or feed forward to uplift the third order intercept point by at least 3 dBs. In addition, we are developing a stacked digital RF amplifier for enhanced power efficiency and flexibility, and this will be showcased at the IEEE Radio and Wireless Week in January 2022. Finally, our fourth research challenge is in the field of secure dynamic spectrum access, driven by the need to enhance spectrum utilization in the lower frequency bands, as echoed in the recent work of the Spectrum Policy Forum for DCMS and reported in this public consultation. So as I mentioned, SWAN has a rich mix of theoretical, analytical and experimentally driven research. So let's now take a look at our testbed activities. At both Bristol and Roke, we have RF penetration testing facilities with screened enclosures and conductive testing, allowing us to subject various candidate wireless technologies to cyber attack. Within the Bristol setup, we can also capture RF waveforms, convert these back to IQ baseband for further analysis, including RF fingerprinting. This is complemented by a rollout in the Clifton campus at the University of Bristol of LoRaWAN technology. Here we have 3 access point locations and over 20 static deployments of sensors. I will say more about this a little later on. So let's now take a look at our RF penetration testbed set up for some RF jamming attacks. So with LoRa using 868 MHz here in the UK and an operational network in Bristol, we need to do this through a cabled test. Also, the transceivers themselves need to be placed in shielded boxes, and we have the transmitter here and the receiver over here. They're cabled through via attenuators to the external port on the shielded enclosures, and in the cabled connection between the transmitter and receiver we have a couple of observation ports and an injection port for our interference. In terms of the signal observation, we can observe the
the spectrum on this vector signal analyzer, and we can also look in the time domain at the actual LoRa transmission. And in the signal on the screen there, we've actually got the LoRa burst being captured in the time domain, and we can drill into this burst and look at all the LoRa parameters and extract the frame synchronization and so on. So what we're going to do now is just set up a very simple RF jamming attack using our arbitrary waveform generator. We've got the link established under the little Arduino processor, which allows us to set up various parameters such as the AGC, the spreading factor, and also pull back the bit error rate. So using the control panel for the ARB, we can switch on the interfering signal. You can see this on the blue trace here, and on the spectrum analyzer we can now see that there's interference present along with the chirp. Now, as expected, this is chirp sped spectrum, so this is pretty robust against CW jamming, more susceptible if we've got some synchronized interference.
This is the equipment set up for a synchronized waveform jamming attack on a LoRa link. Again, our PXI PC is used to control our instrumentation under a MATLAB script, as well as providing a window onto an Arduino Nano, such that we can set the link parameters of LoRa, as well as look at the link performance back coming from the receiver. Jamming synchronization is achieved by the means of a pulse from the LoRa transmitter, which is applied with variable time delay to enable the ARB to play out the candidate waveforms. By observing the link performance, the optimum waveform and timing point can be found such that data communications is lost for minimum jamming power.
So we're now going to look at the RF penetration testbed, again using LoRa, but for this time we're going to capture some RF waveforms, and we're doing that using this vector signal analyzer here and pulling the waveforms back under MATLAB control, and then we can actually take the digitized waveform and analyze that in post-processing.
From the captured RF waveforms, we can extract the IQ stream from a selection of SODAC LoRa modules in the lab. Conversion to the frequency domain allows us to examine the LoRa phi, clearly showing the up chirps and the down chirps of this narrowband chirp sped spectrum signal. With a little more effort, we can identify the frame structure, the preamble, frame sync, start of frame delimiter, and then the data packet burst. Back in the time domain, we can look at individual chirps and plot these on a constellation diagram. We can see constant envelope modulation from the chirp, but more importantly, we can actually see the chirp startup. If we take a series of chirps now from the data packet and overlay those again on the same constellation diagram, the startups do not overlay on the constellation diagram due to carrier frequency offset in each of the modems. So we've taken a series of 5 SODAC units as well as our ARB replaying the LoRa waveform. And you can see by eye that these are all slightly different. So can we use this to identify if a particular sensor has been replaced by a rogue device in the network, i.e. a cyber attack has occurred? Here, machine learning will have a key role to play. So we've taken our captured data sets and we fed those through a neural network with the goal of producing 2D self-organizing feature maps. If we allow this to evolve over a short period of time, noting what you are seeing has been slowed down, we obtain a characteristic feature map for each of the 6 LoRa devices. This seems to be a fairly good marker for identifying individual LoRa sensors. We are currently working on enhancing our fingerprinting methodology by applying convolutional neural networks. to make the fingerprinting more robust. We believe that our method will be completely independent to any phi-mac spoofing applied by an adversary. Clearly, the results have been for conducted tests in the laboratory. So we need to make this applicable to wireless sensor deployments in the city, adding the wireless channel initially through real-time emulation in the laboratory. We believe that the device fingerprint just described, combined with the spatial channel temporal response, will be a unique descriptor for a specific location and device. Exploiting this type of information for wireless sensors in critical infrastructure will aid cyber intrusion detection. So let's now return to our Clifton campus LoRaWAN deployment with 3 access point locations at our Students' Union, the Merchant Ventures building and physics. Notably, the physics deployment has been configured with 2 access points with antennas orientated on plus or minus 45 degrees so we can extract the polarization dependencies from the channel. For each of our static sensor locations, we have a sensor at street level, thus capturing wireless variations due to the motion of people and vehicles, as well as a sensor higher in the building, away from localized motion, as shown on the left for the deployment in Beacon House. This allows us to capture the reported SNR level from multiple static sensors at multiple locations for both busy and quiet times in the city over many months. The datasets will allow us to determine if a simple measure such as signal-to-noise ratio and the statistical variation of that measure as a function of the time of day is a sufficiently good marker for rogue sensor deployment detection for some less critical applications. I can now share with you some preliminary measurements taken in July this year by an MSc project student using some handheld sensors at various locations in the city prior to the rollout of the fixed sensors I've just described. Firstly, for the area adjacent to the Students' Union, we can see that the observed SNR lies within the range 7 to 10.3 dBs. For mobile sensor measurements close to physics and observed from the Students' Union access point, we have a greater range of SNR values from -1 up to 6.8 dBs. Finally, for a series of measurements near to Brunel's Clifton Suspension Bridge, we have a lower set of values from -4 to 3.3 dBs, as observed from the Students' Union, noting that this location was actually off the bore site of the reception angle of the access point. So introducing a rogue sensor with the correct MAC headers, etc., but with the wrong physical distance and location to an access point can be detected from this dataset. But the handheld sensors do exhibit signal variation due to the student-induced antenna orientation, hence the deployment of the static sensor campaign I described previously. Also, these static sensors are really more synonymous with LoRaWAN use cases. So now on to some points that you may wish to take away from this presentation. RF cyber attacks are a threat we must consider given the increased use of low-cost wireless sensors in so many applications, with SLOAN developing techniques to detect and mitigate these attacks. It is also important to understand the weaknesses of candidate wireless technologies to jamming, in particular that of synchronized jamming attacks. SWAN is developing and showcasing techniques for rogue wireless sensor detection based on both a simplistic signal-to-noise ratio measurement and a more complex method of RF fingerprinting from the composite device and channel response. In both of these methods, machine learning will be a critical tool or friend in our analysis. Now, bringing this presentation to a close, if you would like to learn more about SWAN, please sign up to our quarterly newsletter using the QR code now showing. And I'll be happy to answer some questions now, or if you wish to contact us post-event, please use the contact information now showing.